Hello everyone, this is Mr. H again and welcome back to my YouTube channel. In this video, I will be discussing with you solving exponential equations. But first, let's have a quick recap of some important rules that we will be applying in solving exponential equations. So the very first rule is what we call the product rule. For example, we have x to the power of m times x to the power of n will be equal to x to the power of m plus n. So basically, if you are multiplying with the same base, what you need to do is to just copy the base and simply add their exponents. The second rule is what we call the quotient rule. From the name itself, quotient, so definitely the mathematical operation here is division. So if you are dividing exponential expressions with the same base, for example, you have x to the power of m divided by x to the power of n. So what you need to do is to just simply subtract their exponents. So this will be equal to x to the power of m minus n. So the third rule that we need to recall is what we call the power of a power rule. So say for example, we have x to the power of m to the power of n. So basically we have here a power that is raised to another power. And if you have this, definitely what you need to do is to just simply multiply the powers. All right, so it's going to become x to the power of m times n. And for the fourth rule, we have what we call the power of a product rule. So power of a product. So we're looking at, for example, we have x times y, which is the base, and the power, say for example, is it's raised to m. So we have the base here, which is x times y. Both of the factors are raised to m, which is the power or the exponent. So what we need to do here is to simply distribute the power to every single factor inside the bracket or the base, okay? So this is going to be x to the power of m times y to the power of m. For the fifth, power of a quotient rule, okay? So maybe here you're getting the concept of how it's going to look like. So quotient, right? So basically the base here involves division. So for example, our base is x divided by y, and the power or the exponent is m. So basically same with what we did with the previous one. So we will be distributing the power to every single expressions in the base, okay? So it's going to be x to the power of m divided by y to the power of m. All right, so for the next rule, we have the negative exponent rule. So negative exponent rule, so from the term itself, negative exponent. So for example, we have x to the power of negative m. So in order for the exponent to become positive, so this will become 1 over x to the power of m. So the next rule is what we call the fractional exponent rule. So from the term itself, fraction, definitely we're looking at an exponent that is a fraction. So for example, we have x to the power of m over n. So this one is equal to the nth root of x to the power of m. So if you notice the positioning, so the exponential, I mean the fractional exponent, definitely the numerator of the fraction is the power of the base, and the denominator of the fraction is now the index. We call that the index. Root, for example, square root of 5. So that square root of 5 is actually equal to 5 to the power of 1 over 2. So this one has 2 in here as the index, so that's the denominator, and 5 inside, which is the radicand, so it's raised to 1. So that is the numerator. So square root of 5 is technically equal to 5 to the power of 1 half. So the last row is, I'm sure everyone is aware of this. So we have the zero exponent row. So any number that's raised to 0 will be equal to 1. These are the rules of exponents that we will be applying in the concept of solving any exponential equations. Even when you are dealing with only simplifying exponential expressions, definitely all these rules must be followed. I'll be going over 3 different examples in which we will be covering, if not all the rules, will be some of the rules of exponents. All right, let's jump straight into the very first example. For example number 1, solve the equation. So we were given 4 to the power of 3x plus 1 equals 32 to the power of x. Okay, so the left-hand side of the equation has a base of 4 and the right-hand side has a base of 32. So the next thing that comes to mind should be rewriting 4 and 32 to the same base. So basically 4 is the same as 2 to the power of 2. And 32 can be written as 2 to the power of 5, right? And that's what we will be applying when we solve this equation. So let's jump straight to our solution. So here, so we're going to write 2 to the power of 2 times 3x plus 1 will be equal to 2 to the power of 5. So we're just rewriting 32 to 2 to the power of 5, then multiplied by x. X is already there as an exponent. And then from here, you can see that both sides are written with the same base of 2. You can also jump straight into getting everything in the exponent because they're already, both of them have the same base already. So we can just take their exponents. So from here, we have 2 times 3x plus 1 equal to 5 times x. So 2 times 3x is 6x, 2 times 1 is positive 2, and then 5 times x is 5x. And then solving the equation, we'll have 6x minus 5x equal negative 2. So 6x minus 5x is x equals negative 2. So the value of x in the equation is negative 2. Now, if you want to check if the value of x that you got is right, then what you need to do is to simply plug in the value of x, which is negative 2, to the original equation, and then simplify the left-hand side and the right-hand side, and you will be arriving at a balanced equation, which is a true equation. If that happens, definitely that only tells us that the value of x that we got is correct. All right, so I'll leave you to it to check. Second example, solve the given equation. 7 times 2 to the power of k minus 3 minus 56 equals 0. So same with the first example. This is kind of a straightforward question. So we need to find the value of k here. Okay, so let's have a look. If you notice, we were given a constant term. Initially, it was negative 56. Now, so whenever you see something like this, definitely what you need to do is um, maybe try to work out that part. So maybe something can be done with the constant, because noticing that the given equation we have here 7. 7, which is another factor. These two factors belong to one term. So definitely we're talking about two separate factors here. So 7 times 2 to the power of k minus 3. But this one is a separate term, which can be moved to the right-hand side. So let's start writing the solution. So we have 7 times 2 to the power of k minus 3. And then from here, you can see these are factors. Since they are factors, definitely we can divide both sides here by 7. So 7 divided by 7 is 1. So basically, the left-hand side, we're going to have 2 to the power of k minus 3. 56 divided by 7 is 8. All right, see from this line, definitely you can see, oh, 8 can be rewritten 2 to the power of 3. And the left-hand side already has a base of 2. So definitely we can just retain that. And the right-hand side can be rewritten as 2 to the power of 3. And since both left and right have the same base of 2, we can just take their exponents, their power. So k minus 3 equals to the exponent of the right-hand side. We have 3. And then from here, we can solve for the value of k, which is k equals 3 plus 3. K equals to 6. So this is the value of k that will satisfy the exponential equation. So let's head on to our very last example. And so we have 7 times 3 to the power of n plus 1 minus 5 to the power of n plus 2 equals 3 to the power of n plus 4 minus 5 to the power of n plus 3. There are terms that have the same base of 3, and there are also terms that have the same base of 5. So having that thought, you need to be able to arrive at, okay, so let me group those terms with the same base, and you take it from there. So let's group them first based on the same base. So we can say 7 times 3 to the power of n plus 1, and I'm going to be grouping it with 3 to the power of n plus 4. So this term actually is moving to the left hand side of the equation. That will make it negative 3 to the power of n plus 4. So the right hand side of the equation, this term, negative 5 to the power of n plus 2, moves to the right hand side. That will make it positive. So 5 to the power of n plus 2. So this term stays on the right. So nothing changes. So negative 5 to the power of n plus 3. And since you're able to group them, it will be easy for you to actually see the next step. For the left hand side, we can take out 3 to the power of n plus 1. Okay, 3 to the power of n plus 1 can be taken out. So when we factor out 3 to the power of n plus 1, definitely from this term, only 7 will be left. And taking out 3 to the power of n plus 1 from here, it's going to give us 3 to the power of 3. You have to remember the rule. So if you do the reverse process, so multiplying this 2 So say 3 to the power of n plus 1 multiplied by 3 to the power of 3, it's going to give you, copy the base 3 and add their exponent. So n plus 1 plus 3. So 3 to the power of n plus 4. So you're going to go back to the original expression of 3 to the power of n plus 4. So that's why we recalled the roles earlier. All right, so this is the factored form of this expression on the left. So we will apply the same concept on the right. So for the right-hand side of the equation, we can factor out 5 to the power of n plus 2. 5 to the power of n plus 2 can be factored out. So if we take this out, definitely from this term, we're going to have 1 will be left because 1 times 5 to the power of n plus 2 is 5 to the power of n plus 2. And so taking out 5 to the power of n plus 2 from this, definitely there will be 5 that will be left. So don't get confused because this 5 is equal to 5 to the power of 1. So if we're going to do the reverse process, so it's going to give us 5 to the power of n plus 2 times 5 to this is to the power of 1. So since you're multiplying with the same base, based on the rule, the product rule, copy the base 5 and add the exponent. So x n plus 2 plus 1, 1 is from here, which will give us 5 to the power of n plus 2 plus 1 is 3. And you go back to the original expression. And then from here, you can see we need to simplify everything that's inside the parentheses, right? So this is 3 to the power of n plus 1. So 7 minus 3 to the power of 3 is 27. So 5 to the power of n plus 2. 1 minus 5 is negative 4. So 3 to the power of n plus 1. 7 minus 27 is negative 20. Will be equal to 5 to the power of n plus 2 times negative 4. And then from here, you decide which one you want to manipulate first. So either you want to manipulate the one on the left or on the right, it doesn't matter because you will be arriving at the same answer at the end if you do the math right. Okay? So say for example, we divide both sides here by negative 20. So this one will become negative 20 divided by negative 20 is positive 1. So basically the one on the left hand side will have 3 to the power of n plus 1 equals to 5 to the power of n plus 2. So negative 4 divided by negative 20 is equal to 1 over 5. All right. So if you take a look at the right hand side of the equation, you can see that something can be done in here. All right. So we can rewrite the expression on the right. So we copy the one on the left and the expression on the right, we can try to rewrite it, okay? So this 5 to the power of n plus 2 can be rewritten as 5 to the power of n times 5 to the power of 2 based on the rule, product rule. So same base of 5 and you simply add their exponents, n plus 2 is the same. But do not ignore the other factor, which is 1 over 5, the expression on the left. And then here you can see 5 to the power of n is retained. So 5 squared is 25 times 1 over 5. And you can see that 25 times 1 over 5, this can be simplified, correct? So this one can be 25 divided by 5 is 5. All right, so let me erase that. So write the simplified form. So again, 25 divided by 5 is 5. 5 or simply 5 to the power of 1. And we can put this back together again. Rewrite it as a single exponential expression. So 3 to the power of n plus 1 will be equal to 5 to the power of n plus 1. Oh, so from here you can see they have different bases. This one has a base of 3, this one has a base of 5, but then again, you can see that their exponents are the same. And we're going to go back to one of the rules that we have earlier. So from here, basically, what we can do is we can divide both sides by, okay, say we can divide both sides by 5 to the power of n plus 1. All right. So I divided both sides by 5 to the power of n plus 1, and this will become 5 to the power of n plus 1 divided by 5 to the power of n plus 1 is equal to 1. Okay, so if you can recall one of the rules earlier, so the left-hand side, which is this one, can be rewritten into 3 over 5 to the power of n plus 1. So that's one of the rules because both of them have the same exponents of n plus 1, definitely we just take 3 over 5 as the base. Yeah, so 3 over 5 as the base to the power of n plus 1 equals 1. You know that 1 can be rewritten as well as 1 can be rewritten as 3 over 5 to the power of 0, right? Because any number that is raised to 0 is equal to 1. So basically, in order for you to have the same base here, then we use whatever the base is on the left-hand side, right? So we use the 3 over 5, the same base, and raise it to 0. And any number raised to 0 will be equal to 1. And now, at this stage, you already got the same base, so definitely what you need to do is to just take their exponents. N plus 1 equals 0. So n plus 1 equals 0, which is n equals negative 1. All right, so that's all for this video. If you learned something new, please give me a thumbs up. You can also share the video. If you haven't subscribed yet to my YouTube channel, so please do so and help me reach 1001 subscribers by the end of April. So that's the goal. By the way, thank you very much for supporting my channel, and I'll see you on the next video.